For years, something strange has been happening at the edge of our solar system. A group of icy objects far beyond Neptune are drifting in the same direction. Their orbits are aligned in a way that suggests a massive object is shepherding them into a clustered pattern. This alignment is statistically unlikely without an external gravitational influence. And no, it's not Neptune, it's not Pluto. It's something much farther, much heavier, and completely hidden. Astronomers call it Planet 9, a mysterious world that could be 5 to 10 times bigger than Earth, orbiting so far out that sunlight barely reaches it. And the weird part? There are new signs, from old data, new discoveries, and strange objects that might finally point to where it's hiding. Or maybe we've been wrong the whole time. Has Planet 9 finally been spotted? Or is this the biggest scientific ghost hunt of the decade? Let's find out. Back in 2016, something strange caught the attention of two astronomers, Mike Brown and Konstantin Batygin. They weren't looking for a new planet. They were just trying to figure out why some objects in the outer solar system were acting weird. These weren't planets or comets. They were what we now call extreme trans-Neptunian objects, or ETNOs for short, frozen rocks orbiting way beyond Neptune. But the odd thing was this. Many of them had orbits that weren't random. Instead of being scattered in all directions, their paths were clustered. They were all tilted in a similar way, and they all seemed to point in the same general direction in space. That's not supposed to happen. In a stable solar system, small objects that far out should have chaotic, scattered orbits, not neatly aligned ones. The only explanation that made sense at the time. Something massive was tugging on them. Something we hadn't seen yet. Brown and Batygin ran the numbers. If this mystery planet existed, it would have to be at least 5 times more massive than Earth, maybe up to 10. And its orbit would be huge, something like 400 to 800 times farther from the Sun than Earth. For comparison, Neptune is only about 30 times farther than Earth. So this thing wouldn't just be far, it would be in a part of the solar system we've barely looked at. They called it Planet 9, not just because it would be the 9th planet after Pluto was reclassified, but because no other explanation matched the data. And coming from Mike Brown, the guy famous for getting Pluto kicked out of the Planet Club, this was a bit ironic. But this wasn't just speculation. They didn't claim Planet 9 existed just for headlines. Their paper laid out the math. It showed how the gravitational pull of this hypothetical planet could account for the clustered orbits of these distant objects. In fact, they said it could even explain some tilted orbits of known objects, like the way some smaller planets lean in strange directions. That kicked off a worldwide hunt. Telescopes began scanning the skies, trying to find this invisible giant. Astronomers started going through old data, hoping they might have already captured it without realizing. Even amateurs joined in, using online databases, algorithms, and even citizen science platforms to look for anything suspicious. And for a while, it seemed like the more we looked, the more pieces fit the puzzle. More ETNOs were found. Some of them had similar alignments. A few even had retrograde orbits, moving in the opposite direction from everything else. And again, the math seemed to point to the same idea, something big, far away, and hiding in the dark. But there was a problem. No one had actually seen Planet 9. Years passed, more predictions came out, and more search areas were ruled out. But every image, every scan, every attempt to spot it turned up empty. Still, the clustering was real, and every time a new trans-Neptunian object was found that fit the pattern, it gave the theory more weight. At this point, the evidence wasn't proof, but it was strong enough that Planet 9 became one of the most talked about ideas in planetary science. Not because it was exciting, but because it was the only explanation that made the math work. Still, not everyone agreed, and that's where things started getting complicated. The idea of Planet 9 didn't stay unchallenged for long. In science, it never does. As soon as the theory gained attention, researchers around the world started trying to test it. Some tried to confirm it, others tried to break it. That's how science works. If something's true, it should survive every attempt to prove it wrong. So, what did they do? They ran simulations, a lot of them. Using powerful models, researchers recreated the solar system, but this time with a hidden ninth planet, far beyond Neptune. They added the right mass, distance, and orbital shape based on what the theory predicted. And in many cases, it worked. The simulations showed the same kind of orbital clustering we see in real data. The weird behavior of those distant icy objects made more sense when Planet 9 was included. But then came the first major pushback. Some researchers, including Samantha Lawler and Jean-Marc Petit, argued that the clustering might not be caused by a hidden planet at all. It might just be a coincidence. Their point was this: the number of objects we're talking about is small, and most of them were discovered by just a few surveys using the same parts of the sky at similar times of year. That could introduce a bias. If you only look in one direction, you'll only find objects pointing that way. It's like standing in a forest with a flashlight, pointing it at one spot and saying all the trees are in that direction. Maybe, or maybe that's just where the light's shining. This led to a growing divide. Some scientists stayed confident, saying the clustering was too consistent to be random. Others weren't convinced. They wanted better data, a bigger sample of objects, and wider sky coverage before accepting a whole new planet. Meanwhile, more simulations were being done, not just to support Planet 9, but to explore alternatives. One group proposed that maybe the strange orbits are caused by a massive disk of small objects acting together, a kind of gravitational soup pulling on things in bulk. Another group floated the idea that passing stars in the early history of the solar system might have thrown everything off. And then there's the modified gravity camp, a small group who believe maybe we don't need a planet or a disk at all. Maybe gravity itself behaves differently at large distances. Most scientists don't buy that last one. But the point is, Planet 9 was never the only explanation. It was just the cleanest one that matched the math. And yet, the longer it went unseen, the more critics started asking, if it's out there, why haven't we seen it? That question became louder over time, especially because despite predictions narrowing down where Planet 9 should be, telescopes kept coming up empty. Huge portions of the sky were searched, and still, nothing. The theory wasn't dead, but it wasn't getting stronger either. It was stuck in a strange place. There was still no better explanation for the clustering, but the absence of direct evidence was starting to wear people down. That's where things stood for a while. But then something unexpected showed up. Not in the sky, but in old data from decades ago. And it changed the story. For a theory that started with so much energy, the search for Planet 9 eventually hit a wall. Not because the math fell apart, but because the sky refused to cooperate. After the 2016 proposal, astronomers all over the world began scanning the areas where Planet 9 was predicted to be. Brown and Battigan had used models to estimate its orbit. Not an exact position, but a pretty good guess about where it might show up in the sky and how bright it could be. That was enough to kick off a series of targeted searches using the best tools available. Pan-STARRS, the Subaru telescope, the Dark Energy Survey, and even archived data from the WISE mission. But they found nothing. Part of the problem is how incredibly faint Planet 9 would be. If it exists, it's likely hundreds of times farther from the Sun than Earth is. So it reflects almost no sunlight. At that distance, even a Neptune-sized object would be nearly invisible to most telescopes unless you know exactly where to look. And Planet 9 wouldn't be moving quickly either. It would drift slowly across the sky, over weeks or months, which means most software designed to spot fast-moving objects wouldn't even pick it up. Still, the hope was that maybe Planet 9 had already been accidentally imaged by older surveys. They just didn't realize what it was. So, astronomers started digging into archived data from IRAS from the 1980s, Akari, a Japanese infrared satellite from the 2000s, and WISE, a 2010 NASA infrared mission that scanned the entire sky. These surveys didn't spot a planet directly, but they left behind thousands of mysterious heat sources, small, blurry, slow-moving dots. The problem? Most of those dots were galaxies, noise, or image artifacts. But what if one of them was something more? That didn't stop people from being interested, though, because even if it wasn't the Planet 9, it still raised questions. How many unknown objects are hiding in this region? What else could be out there that we've missed? Meanwhile, other surveys kept narrowing things down. In 2021, a team analyzed data from the Zwicky Transient Facility, which had taken years of wide-field images of the northern sky. They filtered for slow-moving objects with the right brightness and distance. The result? They ruled out over half the region where Planet 9 was expected to be, at least for anything brighter than magnitude 21.3. Then came Ceneos 14, a lesser-known but specialized survey that also found nothing. Which meant this: if Planet 9 exists, it either has to be extremely dim, hiding in the far southern sky, or its orbit is so different from what we expect that we've been looking in the wrong place the entire time. In other words, the evidence didn't disappear, but the trail got cold. The more we looked, the more we ruled things out. That's not failure. That's how science works. But it also meant we were running out of places to look, until something new appeared, not just in the data, but in the real sky. A strange, newly discovered object that raised a whole new set of questions. After years of nothing but dead ends, the last place anyone expected progress was in old data from cold, outdated satellites. But that's exactly where the most interesting lead came from. These satellites weren't built to find planets. They were designed to scan the sky in infrared, looking for stars, galaxies, dust, and heat sources. But thanks to how deep and wide they looked, the datasets became a kind of digital fossil bed, a place where something missed the first time might still be hiding. In early 2025, a fresh analysis of both IRAS and Akari archives spotted something strange. It was small, it was faint, but it was there, in both sets of data, about 20 years apart. And more importantly, it had moved, very slowly. But it moved. This motion was the key. Galaxies don't move like that, stars don't, noise doesn't. But distant objects in the solar system do, especially ones as far out as Planet 9 is predicted to be. At first glance, this seemed like exactly what astronomers had been waiting for. A possible direct detection. The object wasn't bright, but it was consistent with what you might expect from a cold planet hundreds of astronomical units from the Sun. It had the right kind of infrared signature. Not hot, not noisy, just slightly warm, like a frozen planet radiating leftover heat. Naturally, this caused a spike in interest. News headlines jumped on it. Articles speculated whether this was finally it, the long-awaited confirmation. But the excitement didn't last long, because the orbit didn't match. Planet 9's predicted orbit is elongated, yes, but relatively flat, tilted maybe 15 to 30 degrees from the solar system's main plane. This new object, it was tilted over 120 degrees. That's not just a slight difference, that's basically upside down compared to everything else. It was moving in a retrograde orbit, meaning it was going the opposite direction of most planets, and far more tilted than Planet 9 was ever expected to be. That's a problem. Could Planet 9 have an orbit like that? Technically, sure, anything's possible. But it would mean all the original models, the ones that predicted the clustering of distant objects, would have to be completely rethought. It would no longer explain the same patterns. And if it doesn't explain the clustering, it can't be Planet 9. It would be something else entirely. Mike Brown, one of the original Planet 9 theorists, came out quickly to clarify. He said it's definitely not our Planet 9. In his view, the object is real, maybe a large trans-Neptunian body or something we've never classified, but not the one they've been looking for all these years. So, in a strange twist, the most interesting object found in a decade might not solve the mystery, But make it worse. Because now we have two problems. We still haven't found Planet 9. We've just discovered something else that doesn't fit. That's the uncomfortable position this discovery leaves us in. It's progress, but in the wrong direction. But not everyone sees it as a dead end. Some argue this only shows how little we understand the outer solar system. Maybe there are dozens of unknown objects like this. Maybe Planet 9 isn't the only one out there. Maybe the solar system is weirder than we thought, and we've barely scratched the surface. And this raises a bigger question. If we're finding strange things just by going back through old data, what else have we missed? Because while this object might not be Planet 9, it proves one thing. There's something out there. While attention was on the infrared mystery object, another curveball came from the far reaches of the solar system. This time, not from old data, but from a brand new discovery. 2017 OF201. On paper, it didn't seem like much at first. Just another distant dwarf planet added to the growing list of extreme trans-Neptunian objects, but its orbit immediately stood out. This thing was on a ridiculously elongated path, stretching out to nearly 1,600 astronomical units at its farthest point from the Sun. For comparison, Pluto only reaches about 49 astronomical units. This object was operating in a completely different part of the solar system. The orbit was not just far, it was extreme. Long, stretched, tilted, the kind of orbit that screams, "Something powerful must have put me here." And naturally, people ask the obvious question, was this more evidence for Planet 9? At first, it looked like it could be. After all, Planet 9 was predicted to cause orbits just like this, flinging objects into weird, high eccentricity paths through gravitational nudges over millions of years. So, 2017 OF201 felt like the kind of smoking gun everyone had been waiting for. But then came the closer analysis. And things didn't line up. Its orbit didn't match the same clustering that the original Planet 9 theory was built on. In fact, 2017 OF201 seemed to be out of sync with those earlier objects, almost like it was operating under a different set of rules. It wasn't aligned with the rest. It didn't reinforce the pattern. It broke it. And that led to a new problem. If Planet 9 is supposed to explain the clustering of extreme objects, but then we keep finding more that don't fit the pattern, does that weaken the case? That's the uncomfortable part. Each new object we discover out there should, in theory, either strengthen or weaken the Planet 9 argument. The more objects that follow the expected pattern, the more confident we become. But when something big like 2017 OF201 shows up and doesn't fit, it starts to raise doubts. Are we really seeing a consistent gravitational influence? Or are we cherry-picking the ones that match and ignoring the ones that don't? Some researchers began suggesting that maybe the pattern itself is a statistical illusion, a kind of observational bias caused by where and how we search the sky. They argued that 2017 OF201 is exactly what you'd expect if there wasn't a Planet 9. Just a bunch of random scattered orbits caused by billions of years of minor interactions, galactic tides, and chaotic motion. That doesn't mean Planet 9 is ruled out. It just means that not everything weird in the outer solar system can be automatically blamed on it. Still, it's hard to ignore the fact that 2017 OF201 exists. Something put it there. And whether that something is Planet 9 or a passing star from millions of years ago, or even just long-term gravitational drift, it's a clue. But not the kind that solves the puzzle. The kind that makes it harder. This discovery also added weight to a different idea. Maybe we're looking for one big planet, when the truth is messier. Maybe there's a population of medium-sized rogue objects out there. Not massive enough to be planets, but enough to stir things up. If that's the case, Planet 9 might not be real, but its effect could be. At the very least, 2017 OF201 reminded everyone of this. We still know very little about what's out there. Every new discovery adds data, but not always clarity. Sometimes the mystery just gets deeper. Let's say Planet 9 is real. A massive world, 5 to 10 times the mass of Earth, orbiting hundreds of times farther from the Sun than we are. The next question is simple. How did it get there? Because it shouldn't be there. According to how planets normally form, there simply wasn't enough material that far out in the solar system to build something so massive. Beyond Neptune, the Sun's influence weakens. The disk of dust thins out and everything slows down. You might get icy rocks or comets forming, but full-blown planets? That's a stretch. So if Planet 9 didn't form out there, where did it come from? One of the leading ideas is that Planet 9 formed much closer to the Sun, maybe somewhere around the same region as Jupiter or Saturn. During the early chaotic days of the solar system, planets were constantly pushing and pulling on each other, exchanging angular momentum like bumper cars in slow motion. In that chaos, it's possible that Planet 9 got kicked out, flung into the outer solar system by a gravitational interaction with one of the gas giants. But instead of flying off into interstellar space, like most ejected planets would, something unusual happened. It got caught. It didn't escape completely. It ended up in a highly elongated, stable orbit far beyond the other planets. It became a kind of solar system exile, too far to be seen but close enough to remain bound by the Sun's gravity. This idea isn't just a guess. Computer simulations have backed it up. When researchers run dynamical models of early solar system formation, they often see outcomes where one or two planets get kicked out into distant orbits. Some even end up in orbits similar to what Planet 9 is supposed to have. It's not the most common result, but it's not rare either. According to some simulations, about 1 in 10 early solar systems could end up with a Planet 9-like object. But there's another scenario, one that's even more interesting. Instead of being born in our solar system and thrown outward, maybe Planet 9 was never ours to begin with. Imagine the early Sun forming inside a dense stellar cluster, surrounded by dozens or even hundreds of other baby stars, all forming from the same cloud of gas and dust. In that crowded nursery, planets and debris would have been flying everywhere. And in those chaotic conditions, it's entirely possible that our Sun stole a planet from another star. This idea, called planetary capture, isn't just theory. Simulations show that in a dense cluster, passing stars can grab rogue planets, or even rip them from each other's orbits during close encounters. If Planet 9 was originally orbiting another star, and our Sun passed close enough at the right time, it could have been pulled into our system and trapped in a wide, distant orbit. In fact, one study showed that the chances of capturing a planet like that during the solar system's first 100 million years could be as high as 20%, if conditions were right. This kind of scenario also helps explain why Planet 9's orbit, if it exists, is so tilted and stretched. It didn't form in the neat, flat plane of the solar system. It came in from outside, and that means its orbit wouldn't match the rest. It would be inclined, odd, unpredictable, just like the clues we're seeing now. Some researchers think both ideas could be true. Maybe a planet formed in the early solar system, got pushed out, and then got nudged further by a passing star. Or maybe several small interactions added up over time. Space doesn't always give us one clean answer, but the key point is this. There are ways Planet 9 could exist, and they're not unrealistic. They don't break physics. They don't require rewriting how planets form. All they require is time, chaos, and gravity. 3 things the early solar system had plenty of. So, while we haven't found Planet 9 yet, we know it could be there, and we know how it could have gotten there. The only thing we don't have is the proof. Yet. After nearly a decade of theories, simulations, and dead ends, the search for Planet 9 is approaching a turning point. Not because someone spotted it yet, but because the tools we've been using so far have reached their limits. We've scanned most of the visible sky, combed through decades of archived data, and ruled out large chunks of where Planet 9 could be. And still, nothing. That's where the Vera C. Rubin Observatory comes in. Located in Chile, this observatory hasn't been fully operational for long, but when it is, it could change everything. Rubin is different from most telescopes. It's not designed to zoom in on one target at a time. Equipped with an 8.4-meter Simoni survey telescope and the world's largest digital camera, it will survey the entire southern sky, night after night, in incredible detail. Its primary mission is called the Legacy Survey of Space and Time, LSST, and it's exactly the kind of project that could finally spot a slow-moving, faint object like Planet 9. Why? Because Rubin is fast. It can capture huge portions of the sky in a single shot. And it's deep, sensitive enough to detect objects much dimmer than what older surveys like ZTF or Pan-STARRS could handle. Most importantly, Rubin will observe the same regions of sky repeatedly over a 10-year stretch. That means it won't just find fast-moving asteroids or comets, it'll catch the slow drifters. The ones barely moving across the sky. The ones like Planet 9. Based on current estimates, Rubin could detect objects as faint as magnitude 24. If Planet 9 is within the predicted mass range and anywhere inside about 800 astronomical units, it should be bright enough to fall within Rubin's reach. Which means if it's out there, and it's not hiding behind the galactic plane or buried in background noise, Rubin should see it. And if Rubin doesn't find anything, that's big too. It won't just be no news. It'll be the strongest evidence so far that Planet 9 either doesn't exist or exists in a way we didn't predict. Maybe it's smaller, farther, or has an entirely different orbit than we thought. In other words, Rubin is more than just another telescope in the search. It's the final test. The one that could end the mystery, one way or another. But the search doesn't stop with Rubin. While it's the most promising tool we have right now, other efforts are still running in parallel. Projects like Backyard Worlds, Planet 9 continue to enlist citizen scientists to look through telescope data, sometimes spotting things that algorithms miss. There are also upcoming space telescopes like Nancy Grace Roman and Euclid that could help indirectly by refining our models of the outer solar system and improving the background maps we use to detect faint motion. And then there's the wild card. Maybe Planet 9 has already been seen, but not recognized. Maybe it's in old data, mislabeled. Maybe it's hidden behind the dense clutter of the Milky Way, where background stars and dust make motion hard to track. Or maybe it's just dimmer than we expected. Smaller, colder, darker. All of these are still possibilities. But what Rubin gives us is something we haven't had before. A clean, deep, continuous survey of the southern sky. And that's exactly where Planet 9 is most likely hiding, according to the latest models. So, for the first time in years, this isn't just about chasing a theory. It's about reaching a decision point. If Planet 9 exists, we're about to know. If it doesn't, we can finally let it go. And that's what makes this next phase so important. Because it's not just about finding a new planet. It's about finishing the story.